Okay, I think we can get started. Can people online hear me?
Hello, yes.
Thank you. And today I'm going to talk about how one does resonance assignments in proteins. This will be kind of a walk through pulse sequences in some way. And then at 2 o'clock, Bruce Johnson is going to do a demo/tutorial of his software, which is called NMR FX Analyst. That, of course, is one of the software packages that you can process and then analyze NMR data in. Right, so these are things we've already talked about. For smallish proteins, one can work with only hydrogen NMR, but then very quickly you run into the size where first you need to do triple resonance experiments with carbon-13 and N15, and eventually labeling with deuterium, trosi, etc. Let's skip through some of this. So the strategy with for unlabeled proteins and labeled proteins are quite different. And that's because they're for an unlabeled protein where you're just using the hydrogen spins, there are no significantly large scalar couplings across the peptide bond. And that means you can use things like COSY and TOXY that we'll talk about to assign resonances within an amino acid, but you can't connect one amino acid to the net scalar coupling. And that means you have to use the NOE to connect amino acids together. And that, of course, has a certain ambiguity because NOEs could be long-range tertiary interactions just as easily as a short-range interaction. So if you have, for example, an NOE from, say, a valine to an alanine, that you might have an alanine next in the sequence, in which case that would be telling you how to link the amino acids, but there may be another alanine very far away in sequence that happens to fold near the valine. And if you think that's a sequential connection, right, you're going to make a big mistake. On the other hand, when we have labeled molecules, N15 and carbon-13, then we have scalar couplings that let us move through the peptide bonds by going from one nitrogen to the preceding carbonyl and then to the preceding C alpha, for example. So that's unambiguous way of connecting the amino acids because it relies on scalar couplings that we know. So the NOE data is purely to do the fold. It's not a part of the assignment process. And then the side chains are assigned with also COSY and TOXY-like experiments, but typically using the carbon scalar couplings rather than proton scalar couplings, because the carbon-carbon one-bond scalar couplings are much larger than the proton-proton three-bond scalar coupling. So, of course, you've seen the spectrum, the COSY of ubiquitin, and these different fingerprint regions, for example, for the aromatic region, the methyls, etc. And then here the spectrum has already been assigned. We talked briefly and you solved the problem about the double quantum filtered COSY. And the main purpose, I can't remember how much we talked about this, why does one do the double quantum filtered COSY? And that has to do with the line shapes close to the diagonal. So you'll hopefully recall from the product operators that the cozy diagonal peaks and cross peaks are 90 degrees out of phase with respect to each other. So here, the cozy has been phased so that the cross peaks are absorptive. They have this kind of four lobe structure, and the diagonal is dispersive. So if you get close to the diagonal, the dispersive tails are of huge interference, and one applies very strong sine bell window functions to try to cut the tails. But of course, that has other distortions in the spectrum. The double quantum filtered cozy, the cross peaks in the diagonal have absorptive phase. And you can see, for example, this cross peak here is almost on the diagonal, but it's clearly a cross peak. Whereas over here in the cozy, right, it's a little hard to decide if that's really cross peak. So, but the two quantum filtered cozy we saw has half the signal. So for doing assignments in unlabeled proteins, you might run just the cozy to get high sensitivity for the cross peaks that are far from the diagonal, like the NH hydrogen to alpha hydrogen, and then use the double quantum filtered cozy up in the methyl and methylene region where the chemical shift differences are much smaller. In the beginning, when this was all, the pulse sequences were being established, of course, if we did a cozy and then connected an amide hydrogen to an alpha hydrogen, the problem would be how do we connect the alpha hydrogen to the beta hydrogens? And there were developed then what was called a relay cozy, in which you would have a second transfer period in order to relay the magnetization another step along the way. And then a double relay cozy would do two steps along the way. So you walk your way along by basically repeated cozy transfers. And the downside to those was the sensitivity was generally pretty low and line shapes would get pretty complicated. So those were largely superseded eventually by what are called oxy sequences or isotropic mixing sequences. And you can see the evolution actually in the first edition of the Cavana et al. Protein NMR spectroscopy book. There's a long discussion of relay cozy and double relay cozy. And in the second edition, they're kind of mentioned in passing, because they're just not run very much anymore. So Hoxie sequences start with, as always, a T1 labeling period to record the frequencies. And then there's the so-called isotropic mixing sequences. And these were designed originally by adapting sequences that were used for decoupling, and then eventually using computer designed sequences designed specifically to do toxic transfer. So three that were specifically designed are shown here: DIPSY2, FLOPSY16, and WRST2, in which what are shown are contour lines of the efficiency of transfer between spins that are separated by some frequency. It gets harder to transfer if the spins have very different frequencies, and obviously we would like to be able to transfer, for example, if we want to transfer from a methyl to an amide hydrogen, that's quite a large frequency band. the mechanism itself, you can work out, by hand what it looks like just for an IS spin system. And that's done somewhere in some of the notes. But that tends not to be very interesting. That doesn't really tell you what's important about the toxie. The important thing about the toxie is it flows the magnetization through the entire spin system. And you can see example calculations here for an isoleucine. So we're looking on the, which one is which? Right, so the first is that we have the sample in D2O, so there are no amide hydrogens. Then we're transferring from the alpha hydrogen out along the side chain of the isoleucine, and you can see the profile is pretty complicated. And there'd be no way to kind of work that out analytically. It's a computer calculation. And obviously depends on what you think all the J couplings are. So I don't remember, we picked some nominal J couplings here. And then the game is to pick a mixing time that kind of gives you what you want. Obviously, these profiles look different for every amino acid. A peculiarity of valines, for example, is the magnetization tends to just zip from the alpha through the beta out to the methyl groups. And then the lower one is if we have a sample in water, and now we're looking at transfer from the amide hydrogen out to the alpha, etc. So you can kind of see here, right, the first thing that happens, magnetization starts to transfer to the alpha. And then as you build up magnetization on the alpha, it starts to transfer from the alpha to the beta, and then from the beta to the gammas, and eventually out through the spin system. And if you look at a bunch of these, you can see that in water, mixing times of 45 and 70 milliseconds are pretty common in the literature. So 45 really emphasizes the transfer from the amide hydrogen to the alpha hydrogen. And then 70 milliseconds, you have reasonable high transfer to all the other. And the downside of going to longer mixing times is, of course, relaxation losses. If you wanted to go out to say 100 milliseconds or longer, that's pretty hard to do. Just because of relaxation loss. Actually, Stephanie Lasser, who works on computational aspects of NMR, has a cute demonstration where up to 4 spins, you can actually work out analytical results. No one but Stefan would ever want to do that because the algebra is so complicated. But it turns out that the solution for up to 4 spins is exactly the same as, this toy where you have the steel balls hanging on strings, and there's 4 of them in this case, and you swing one, and then one bounces, and then they all gradually.
Cradle.
What's it called?
Newton's cradle.
Newton's cradle. So it is. So it turns out that's exactly the same mathematics. So you start first by transferring from ball 1 to ball 2, and eventually ball 4 starts moving. And that's like the transfer from the alpha out to the methyl group. And when he does it, then when you get this toy, all the strings are the same length. But then he uses rubber bands or ties to essentially change the length of the strings to correspond to different J couplings along the way. It's really quite fun.
So maybe you said this and I missed it, but to what extent is that, like the force system dependent on topology?
They all depend on topology.
What I got really interested in years of his life, but I just remember all these end effects, you know.
Yeah. So
20 and 25 cent. All story.
right. So for example, in the veiling, as I said, the magnetization ends up on the methyl groups very quickly. So, you know, for both the cozy, the relay, double relay, and then the toxic, there are papers back in the 80s in which there are graphs like this for every spin system with variations and couplings, etc. So it was a big industry to work this out. Of course, that led to the idea of maybe you could design topology specific pulse sequences that maybe would be more specific for an isoleucine than a leucine, for example, because of the different topology. And there are sequences like that. They've never become tremendously popular because there tends to be a lot of relaxation losses when you're trying to get something to be so specific. But maybe there's an opportunity for smart graduate students to revisit that. So here's just, you know, an example for some lysines, and the mixing time is unwisely not indicated here, but it's probably, you know, 45, 70, and then 100 and something milliseconds in ubiquitin. And you can see in the left panel, you get a transfer from the amide of K48 out to the beta, and you kind of zip through the alpha already. And then out to the gammas. But then as we increase the mixing time, you start to see some transfer to the beginning of getting some transfer to the deltas. And then at the very longest mixing time, you start to see the deltas. You've made it to the end of the chain, but you can also see the signal intensity getting lower and lower. Now, if you look back at the chemical shift distribution, say in biomag resbank, you'll see that here, for example, we have the gammas are at higher frequency than the deltas, and betas are lower frequency than the gammas. But when you look at shift distribution for these long side chains, there can be some overlaps. And the toxi, unless you're very carefully looking at these kinds of curves, it's pretty hard to tell in the toxi experiment which of these peaks is which. So, you know, these days people tend to do it based on these canonical shifts, but that's not a guarantee. If one really wants to be absolutely sure of the assignments of these long side chains, one has to do some double quantum experiments. Not double quantum filters, just straight double quantum experiments. But they're just not done that much anymore. So I would say there's a little ambiguity sometimes for these long side chains. If the only assignments are being made by toxic and canonical shifts. So the cozy and the toxic then gets the side chains linked back to the alpha and the amide. And then the problem is how do you connect to one amino acid to the next. And then, of course, as I said, it has to be done with the nosies. There's a nosy whole sequence with the mixing time. And we've talked about, of course, the problem of spin diffusion, et cetera. So you have to pick what your buildup time is. You've seen the nosy spectrum of ubiquitin. The table seems to be missing. I'll add it in. Vutric in the early days went through crystal structures and tabulated all the distances you would expect to see for consecutive amino acids, out to about 5 amino acids down the covalent chain, depending on whether the molecule was beta sheet, alpha helix, or loop, so that you would know when you were trying to sort out the connections what you expected for the short and medium range NOEs. Because again, as I said, it could be tricky if you start mixing up the long range NOEs with the NOEs that are giving you sequential connections, the whole process goes bad. Why it's really important in doing this in hydrogen only case that you get, virtually all the assignments completed. Because if you say I have 80% of the assignments done, I can't get the rest. Well, the fact you can't get the rest might be telling you something's wrong along the way. It's a little less stringent when we have the label. So even now, unless the protein just is really hard to make, even a protein domain that you could do just by hydrogen, mostly people still label it they can just because it's so less ambiguous. So of course, then we go on to the HSQC, is the fingerprint for N15 labeled proteins, as we've seen this before. Here's an advertisement for Bruce's software that will be coming up shortly. There are lots of variations of HMQC, HSQC, constant time experiments, decoupled experiments, Strozzi experiments. And I think in the interest of getting to Bruce, I'm going to skip most of that. You can look back to all sequences yourselves. There's some of the product operators are worked out for you. So it's past. Of course, before the methylprosy, the HMQC sequence had the problem that the multiple quantum coherence, while it doesn't have J coupling to, say, the nitrogen and the amide hydrogen, that amide hydrogen is in the transverse plane. It has couplings to other hydrogens. In the HSQC, the hydrogen is on the Z-axis, so there's no scalar coupling evolution. And that led to, if you can see it here, if you get very close to the screen, you can see in A, the HMQC, the line shape looks a little different than in the different HSQCs that are shown here. And I can blow that up here. Here's what the pre-induction decay looks like in the T1 dimension. Here is the HMQC for some residue. Here's the HSQC. And here's a constant time experiment. So of course, the constant time experiment doesn't have any decay, but the amplitude of the signal is small because relaxation happens all the time. If we Fourier transform this, here is more or less the natural line width of that amide nitrogen. The constant time is much narrower because, of course, there's not really decay. What we're seeing here is really some decay due to inhomogeneity or possibly small chemical exchange effect that are partially refocused depending on where the constant time 180 is. So this really is not a real line width. But here, this looks kind of nasty. And that's because the coupling evolution gives a dispersive component to the signal. And that dispersive component of the signal basically drills a hole down the middle of the peak, and then the tails of the dispersive signal contribute to the line shape. So before the invention of the methylprosy experiment, the HMQC had become kind of disfavored because of these properties. But you need the HMQC or a variant of it for the methylprosy experiment, but then you also deuterate everything else. So you don't have the problem of these other coupling constants. No. I don't remember if we talked much about aliasing. We did say at some point that this spectral width in either dimension, but here we focus on the indirect dimension, the spectral width is 1 over delta t, the sampling time, the T1 increment. In this particular case, I've shown the full spectrum that I imagine kind of carbon spectrum like. And the middle is this dashed line. And then the sampling time has been set so that these two dashed lines are actually the spectrum that's being sampled. So that there are signals outside the spectrum width that's being sampled, and then they will end up artifactually coming into the spectrum in some new place. And the language is a little bit vague about what this is called. It's called folding or aliasing, and it would be good if we kept them separate as to what they mean, but that's not really kept separate. So depending on how we do the quadrature detection, here, TPPI, which isn't actually used so much anymore, will reflect the peaks outside the range back into the range. And you can see why we don't do this for carbon spectra, because we end up folding that are reflecting carbon signals back on top of each other. States or TPPI states, which is how most experiments are run now. The edges of the spectrum are connected like a barrel or a cylinder. So the signals that are off the bottom reappear at the top. And fortuitously in a carbon spectrum of a protein, that tends to put them in places where they don't overlap. So it's easy then for Bruce's software to keep track of the alias peaks relative to the true peaks and then unwrap them, for doing assignments, etc. Occasionally, I think they fixed most of it now. Occasionally, you would find in Biomag Res Bank some deposition with just some crazy carbon shifts because the authors hadn't unwrapped the whole. You would end up with an alpha, it was at 10 parts per million because it was folded up here and hadn't been unwrapped by the authors. So I think that's pretty much all fit. But they were obvious problems. So here is an example. Here is the C13 of the carbon spectrum with a very large spectral width. So you see the entire spectrum and peaks in their proper position. And then here it is with the spectral width reduced. And now the peaks down here in the lower left are aliased into the upper left. And the peaks up here in the upper right are aliased down into the lower right. But they don't land on top of each other. We adjust things so that they don't land on top of each other, so we can figure out who's who. Now, why do we bother doing this? Why do this, which seems complicated, rather than just, why don't I just do this? Well, suppose I'm going to acquire 128 increments. The resolution is set by the largest T1 by T1 max. So in 128 increments, if I can make the spectral width smaller, delta T is larger, and therefore T1 max is larger. So I can maximize resolution by folding the spectrum. Yeah.
Those folded fields, is with the original, and the intermittent.
That depends how you treat the first point. So if the first T1 point is adjusted to be really zero, right? Then there's no phase correction in T1, and the peaks will all have the same sign. If you would adjust the first point to be half a sampling increment, then you're going to need 180-degree phase, first order phase across the spectrum. But these peaks should have gotten a phase shift of, let's suppose, depends how Bruce's software works, but let's suppose that up here was minus 90 and down here was plus 90 to get 180-degree first order phase. Then these should have gotten the phase greater than 90, but they're going to get a phase less than 90 because they're folded up here. And with exactly a half as well, that makes them exactly upside down. They're exactly getting 180 degrees with the wrong phase. So again, whether that's good or bad, depends on the particular experiment. Many of the Brooker pulse sequences are adjusted so that it looks like you start with 0, in which case these would all be the same phase. That has the advantage you don't accidentally get cancellation. If two peaks get too close to each other, and one's positive and one's negative, right, they're going to start to self-cancel. More HSQCs, product operators. Once we start with the side chains where you have CH2s and CH3s, we have to worry more about how all the different product operators are evolving under the coupling. And hopefully you saw that in the midterm, or you will, where you had to deal with a methyl group. So if we just had an IS spin system, by now you're pretty familiar with the notion that the maximum intensity is going to be 1/2J setting of the sine function. But now you have these much more complicated trigonometric functions to sort out. You were asked to do one by hand, but now, of course, frequently we just do it by computer calculation. This is, I may say something here, this sequence, this FHSQC is the so-called sensitivity enhanced HSQC. And we said most of the time in a 2D experiment, you throw away half the magnetization. Because after T1, you have a cosine term and a sine term, and generally only one of them gets refocus to be detected, and then you have to run a second experiment to get the other component. If the first experiment gave you the cosine, then you run a second experiment to get the sine, but of course, on average, you've thrown away half the signal. So this sequence is an extended HSQC. You can see there's a second to net point period. And that was to refocus the other component. So you would end up with both components recorded. There's a little bit of extra relaxation loss, of course, because of the extra net. But for 20 or 30 kilodalton proteins, that's not very much. So you end up gaining √2 in signal to noise, and that has been many of the triple resonance experiments that use nitrogen as one of the transfer steps use this trick a lot. Not so much with carbon. Now, um, so here's a product operator calculation of how that works. Yep.
So the previous slide,
Where did it go?
the one with the PHSPC. In for the first case, you have continuous rate proton.
Mm-hmm.
Second case is a bypass.
Mm-hmm.
And what determines how you decouple proton?
Right. So in the first one, so here, let's just look at the second one, which is just like normal HSQC evolution. And you have a T1 period and a 1-8. So during that period, if the product operator was, say, IXSZ, during the first T1/2, that's going to evolve under the scale of coupling. And you're going to have a mix of then the in-phase and antiphase operator. And then you have the pulse, and that refocuses the coupling. So that mix goes back to the starting operator. But during the T1 period, then the relaxation is the average of the relaxation for the in-phase operator and the antiphase operator. And unless the protein is highly deuterated, the antiphase operator relaxes faster because the IZ component is a proton operator and it interacts with all the other hydrogens. So, that's not so great. The signal is decaying. Here, the initial inep is followed by another inep to refocus the antiphase operator to in phase. And then the decoupling is used to keep the operator in phase all the time. So the line is narrower, but at the penalty of these extra inep steps. So when you build these into longer sequences, sometimes you can do this trick without complicating the experiment more, in which case it can be kind of for free, that then you can lock yourself with the in-phase operator and gain some resolution. So it wouldn't be so common to do this just as an HSQC because of the extra relaxation losses. And during this period, if you're looking at a CH2 or CH3, more complicated things are happening with the J couplings. So this is more an illustration of how these things get built. And of course, then there's the Trozy experiment that then just picks out the narrow multiple. So the product operators are all worked out for you here. You can check yourself. But one of the things that's interesting is the PEP HSQC was worked out by me as a postdoc. So it's probably my most cited paper. It was almost an accident because I had come to learn NMR. I'd never done NMR before being a postdoc. And Mark Ranson and John Cavanagh had worked out a way to recover both components in an epoxy experiment. And John gave a group meeting about this and said this works because the epoxy signal is cosine modulated. And at that point, I was trying to learn how HSQC worked. The experiments I wanted to do. And at that point, the only thing I knew about the HSQC was that it was cosine modulated. So I figured if they could make it work in epoxy because it was cosine modulated, we should be able to make it work in an HSQC that was cosine modulated. And that turned out to be the case. And fortuitously, anyhow, I worked it out with all the product operators that I just skipped over. And years later, Christian Griechinger pointed out to me that how it really works, you can understand very simply by looking at the energy level diagram. And this is always a good time for me to, remind you that there's many different ways of looking at NMR experiments, and you shouldn't forget the energy level diagram exists. So here, what the FHSQC does is it does a selective 180 across the zero quantum transition. We can't do that with a pulse. We have to do that by a combination of pulses and J couplings. So, but if you do a zero quantum 180, then the signals end up like this. This arrow ends up over here, and this arrow ends up down here. And that's the PEP signal that you want, where you've got both components. I asked Christian if this just was for illustration, and he says no, he has designed pulse sequences in the past by looking at these energy level diagrams and figuring out he needs some selective rotation, and then go back and figure out a pulse sequence that will accomplish that. But he's way smarter than I. Here's how it works if you add gradients. Here's the propagator for the Trozy experiment. And again, if we look at the energy level diagram, it turns out that what the Trozy does is first a selective 180 across the alpha-alpha to beta-beta transition, followed by a selective 180 between the alpha-alpha and beta-alpha. And you can see now, if we go back here, right, both of these coherences have the same sense, right? They're both lowering coherences. And here, they're now in opposite senses. One of these, right, here's I plus S alpha, that's one member of the doublet. Here's I minus S beta, the other member of the doublet. One of these is broad and the other one is narrow because of the Trozy effect. But because one is raising and the other is lowering, we can now phase cycle or gradient select one over the other. And that's just what we do. So, and again, I think I've showed you this before. If we don't decouple, this is what the HSQC looks like. If we decouple in both dimensions, we get the average. And if we do the Trozy, we just pick this one out and get a very big peak. And then here are some example factor in a relatively small protein where the Trozy effect isn't so huge. More gradient selective versions. I better skip on it, but we've already talked about some of this. And what I want to do is then when it comes to triple resonance experiments, of course, now we have virtually infinite possibilities for moving magnetization around. Here's the HMCA. I think when the problem they did in HMCO, is that right?
Yeah.
So this walks you through what's different about building an HMCA rather than an HMCO. The very last part of the problem you did ask, what would be different when you convert them? And one of the main differences is, of course, the relaxation properties of an alpha are very different from a carbonyl because of the hydrogen sitting on the alpha there. So this walks through that sequence. And then, of course, one can keep going on and just keep moving the magnetization around. And by now, hopefully you recognize, right? Maybe it's easier to see here. I start with something that looks like an HSQC. split it into two halves. In the middle, I stick the transfer from the nitrogen to the C alphas. Figure out how to frequency label and couple. And then I'm done. And we can, but it's just a whole series of inepts basically. And we do the same thing with more complicated pulse sequences. It's a series of inepts. Maybe it's easiest here to just end then with the Toxie experiment for doing the side chain. So this can be done as a 3D or a 4D, depending on two different 3Ds or two different 4Ds, depending on where you put frequency labeling. So for example, here, this starts by frequency labeling the hydrogens while doing the net transfer to the carbon. So the total time period here, 2t is going to, or 2 tau is going to have to be 1 over 2j, and it's done in this way to save a couple of pulses. Then we transfer to the carbon. The carbon is labeled in T2. So we've labeled and C and an H that are directly bonded to each other with their two frequencies, the hydrogen frequency and the carbon frequency of the CH pair that are connected by one bond. Then we have isotropic mixing. Now it's through the carbon-carbon couplings, and the carbon-carbon aliphatic couplings are about 35 hertz. The carbonyl is about 55 hertz. So much bigger than the proton couplings that are about 10 hertz. So we can do the transfer much more efficiently, although the relaxation rates are also larger. So here's computations, and you can kind of see something around 20 milliseconds. It's magnetization pretty well dispersed. And now, after the mixing, we come back to the proton, but now this is the destination proton, and we record its frequency. We could do it the other way. For example, we could label this hydrogen frequency, then do the Toxie, and then record the carbon, and then the proton. In which case we would have the labeling of proton and carbon for the destination. And if we did both and had a 4D experiment, then we would have both hydrogen and carbon pairs labeled with their frequencies. And here's just an example then of the walk for the isoleucine along the backbone. If we replace the isotropic mixing with something that looked like the cozy, we would then have basically the cozy, but now the carbon rather than hydrogen. But the same idea is, basically apply. So I think at that point I can let Bruce get set up. Everybody can scratch for a moment while Bruce gets connected. Or maybe you already are connected.
I'm not. I guess
Okay.
I just have this little conceit. I want 4 people.
Let's see, I stopped sharing.
Let's see. So I have to join the Zoom.
Yeah, the Zoom is here. Back in immediately. You want me to polish the fly?
No, I didn't work. I think I'm pretty good.
Does it take this time?
Yes, it does.
So I'll leave it here.
Okay, so in the case.
So that you use power during the Zoom.
Yeah, okay, we'll plug it in then. Sure.
So then by way of introduction, Bruce Johnson is a research professor at City College. CUNY graduate school, however they, you know,
ASRC.
and longtime developer of software for NMR. And he's going to talk about his latest processing package. Once he gets connected.
Once I connect, yeah. So,
While Bruce worries about getting connected, are there any questions online?
No problem.
What do you do about aliphatic stereotyping? The early cooking?
Right, so if we're doing, say, the carbon epoxy experiment, then during T1 or T2, when we're labeling the carbon with the chemical chip, of course, the carbon scale couplings have. And that is essentially a homonuclear coupling, so we can't easily apply 180 degree pulse. So there's two things that are done. One is to keep the maximum evolution period short, so the couplings don't get resolved. And that means you're limited to about 10 milliseconds and evolution time. So resolution isn't so good, but you don't see the coupling, not evolved enough. The other is to do a constant time experiment. And then the constant time experiment would be set to either 28 milliseconds or 56 milliseconds, so that the couplings evolve either by 180 degrees or 360. Ideally, you would use the 58 milliseconds, but generally, except for a small protein, there's just too much relaxation loss. So usually it would be 28 milliseconds. And then you could have some issues between positive or negative, depending on how many carbons that are connected to. Could be a bit of that. But one of those two, probably now, if Shivani was here, she might say, well, you can now use the 58 milliseconds with enough sampling. You don't have to sample every point. Now, occasionally people try to do like selective pulse on the betas, but then the glycines are near the beta and serines are far away. There aren't any really good solutions other than constant time.
So we can have.
Like how do we like speak that off?
The carbon needle you can become. It's far enough away that we can apply selective pulse on carbon.
But one giant.
That's something we should really be out at. Considering the aromatics, you can decouple them.
I get it. Okay.
We're getting close, we think.
Yeah, we're getting there. Just going to share my screen. That's not. Okay, good. Let me find the top. Okay. There's a few people, you guys all ready? Somebody's getting up, running around. Okay. Some of you probably saw a workshop that I did about that, but not all of you. Some people online. Will be a little bit redundant, but I'm going to try to talk about new stuff or different stuff than we did before. Okay, thing one. Okay, so I'm going to talk about our software NMR, and we're going to try to think about, I'm sure some of the things that Art has taught you about in the course, some of the things that Art talked about today, we'll actually look at some of the data sets, backbone experiments, things like that, try to assign the protein, do some processing, I'm sure he's talked about. Sometimes they do this like hands-on, but I think given the time we have, there's people on Zoom, it's most useful hands-on, have people in the room that can walk around and fix things when I break things for people. So I'm going to basically walk through and do, a demo. At any point, get questions. At any point, there are things that you want to see, maybe you use NMR effect, you have questions about it, maybe there's types of data sets that you're interested in processing or looking at or assigning. Don't hesitate to, suggest things, directions to go in, because this is kind of free form. I've got a bunch of data. We're going to walk through, we'll start with some little basic processing and go on. If you want something, which I'm sure you all do want the software, and it's really good, go to the nmrfx.org webpage. A lot of people for many years have used our NMR software. NMRFX it's both a successor and a complement to NMR-VJ. NMR-VJ is really a visualization and assignment tool. What we did with NMRFX is put in all the processing stuff, so you can get up to the point you find the visualization assignment, and the structure calculation stuff, so you can actually calculate structures. With our ring dynamics, you can do NMR dynamics, experiments, stuff like that. So it's, I think it's soup the nuts, or start with your FID and end up with publication. That's the goal. It runs on all the major operating systems. It's written in the Java programming language, so it's very portable. So if you're on Mac, if you're on Windows, if you're on Linux, runs everywhere. Mostly runs through a GUI, but there are things you can do like the structure calculations, command line stuff, where you give it basically a name of some files to do a structure from, and it'll calculate a structure on the command line. If you want to get a copy, you just go to the analyst page, click on download, choose your operating system, macOS. You need actually to register. Or if you've already registered and log in. We do that basically so we can report to the each time we try to get, new grants, how many people have been using it, things like that. If you're on a Mac, newer Macs use an ARM processor or silicon processor that will call their M1 and M3. You want to get a version that has ARM in the name. If you're on an older Intel processor, you get the version with ARM. And same thing, Windows, Linux basically is going to look slightly different, but basically everything's in the same place. So you just download it, put an installer on the installer, and off you go. I would, usually normally going to run it on Mac, you're going to install an applications directory. I will tend to run things from the command line started up because it gives me a little more debugging information, because inevitably things are going to break during demo. That's why I like to do the demos, because I'm always exploring things that I'm not doing on a daily basis. You find issues, and I can see a little bit more about what the problems are. So I'm going to start up here from my command line. Normally would do that. One advantage of doing that, sometimes we want to start multiple copies of the software. In the command line, you can actually start multiple copies and get them going. You actually have separate instances running at the same time. If you double click in the applications folder, they will always just start one. Okay, so we've got it started out. I'll try to go through this quickly, but I'd like to a little bit talk about some of the concepts of the processing. Just to reinforce maybe things that Art has talked about, or Deanna talked about in class. So if we go to the processor, if you haven't opened up a data set, there's a simulator. Over here under the simulation, you open this tab, and then we have a bunch of operations. So let's just simulate a little bit of data. I'm going to go to group operation, and I like that gen to start with. If you've used programs like NMR pipe, you think you write a pipe script to the shell script that has a series of processes in operation. NMR effects is kind of similar in that they're a series of operations. For every operation, you have a series of parameters you can do, so you'll get these are like basic accordion tabs over here. We can sort of open them up. So under effect rough, we can set simulation spectrometer frequency and number of data points. Under gen, we can set the frequency. So let's think about how to scale it. So if you get that, then we can see what happens to change the frequency, obviously. The sound wave oscillates faster or slower. Line width, increase the line width is effectively the same thing as increasing the decay rate. So the signal decays away faster. A lot of operations have a plus or minus button over here. So if you click on the plus button and get wider range to slide down. And so NMR signals exponentially decaying sinusoids. They're characterized by 4 parameters. The frequency of the oscillation, this decay rate, the amplitude, so we're going to make signals higher or smaller, and the phase, basically where it starts. Does it start as a sinusoidal signal like that, starting at 0 and going up, or is it cosine signals? NMR signals are complex. If I click a complex button, you can see the real and the imaginary data. So if we want to process the data set, we need to add more operations. First operation you might do on your FID. Fourier transform first. We could try that. We can add in the Fourier transform and see what happens. So let's go to plus, common operations, Fourier transform. Good. I'll turn off the complex. It's got a little bit of a phase error there. That's actually not really a, phase 0. Okay, all right, so you can see the effect of the phase in the FID translated into the effect of the phase in actual spectrum. Okay. One reason you're often looking often to be for Fourier transform. Line broadening, yeah, okay. So let's think about that. Why do we do line broadening? Let's go back. Let's turn off our Fourier transform. You can see that the signal does not decay away all the way to 0 in the end. That means effectively you've got a discontinuity at the end, this square sort of change in the signal from an oscillating signal to 0. Fourier transform of that gives you signal wiggles on the side of the peak. So we'd like to apodize that. So let's put in an apodization function. So the common operation is apodize. That's introduces apodize. And there's a whole series of different window functions that you can apply to your signal. By default, with the one-dimensional spectrum, I can just turn on exponential decay. You can see this line up here at the top is the shape of that exponential decay, and I can increase the decay, and you see it as I increase it. I'm basically multiplying the FID by that, and I'm driving the end of the signal down to 0. Okay. Any other things that we would do before the FT? Zero fill. Yes. Why do we zero fill? two reasons to zero fill. One is cosmetic. If you add zeros at the end, when you add p, those basically become interpolated points in the spectrum. So you get higher digital resolution. You're not really increasing actual resolution, but you're giving more points to define the signal. But there's a fundamentally more important thing. I don't know if this is gone over in the class. If you don't zero fill at least once, you're effectively throwing away half your signal. That starts, I'm going to the theory here, but basically, your signal is basically starts at time zero. There is no signal before you've actually done the pulse impulse. And it turns out if you work out this theory of signal processing in that, with a complex signal, if you don't zero fill once, you effectively lost half the information in the signal. So you should always zero fill at least once. We could sort of work through a little playing around with the data and sort of reproduce exactly how that works. But in today's talk, I won't go into that. So let's insert a zero filling operation. Yeah, I have to go forward to see that. So if I go up in signal, you can see now I've extended by once. You're going to extend more times, and basically it's going to give you better digital resolution, but not actually true resolution. Turn on Fourier transform. The certain plus and minus when you zero fill. Remember I said that if you didn't acidize and the signal was not zero, you're going to introduce these sig wiggles in the spectrum. I said that and then they weren't there. It turns out that if you don't zero fill, you typically don't see them. So if I turn off the atomization, turn off zero filling, okay, don't see them. If I do zero fill, as I've told you, you should, you now see the thing wiggles, but indeed, I want to turn on the atomization to drive the signals. There are many different formats. We get 1, 2, 3, 4, 5, 6, 7, 8, 9 different atomization functions to do. I'm going to turn off the Fourier transform so we can see the shape of some of these. Exponential decay is the simplest thing. It's basically the same shape as your actual signal, but you basically increase the decay rate goes to zero. All these atomization functions, you're trading off various things. One, we want to get rid of those things where that's fundamentally important. We need to drive that signal to zero again. So there is this discontinuity in the signal. Basically, it's like convolving the signal with a square box and Fourier transform that going to give you these same wiggles. So we need to at least get the signal down to zero. Then we have other factors. When we do the exponential decay, we're basically increasing the width of the line. We're increasing the natural decay of the signal. So that's not good. We would rather not increase the width of our lines. So we can look at other factors. We're also advantageously reducing that amount of noise relatively. So this playing around with the resolution you have, the signal noise, the reduction of these atomization of these think wiggle artifacts. Most common function that people use in protein spectroscopy is probably a Seinfeld window, and often a Seinfeld squared. So you can see under the parameters that I have over here, we have a power by default tube that gives you a Seinfeld squared. You can play around with any of these to see what the shape looks like. 0 and 1, that's a true sine window, that's sine squared. The offset. See if I shift this, it changes it from sine, cosine, or really cosine to sine. This is now building up, starting at 0. Generally, you'd like somewhat the shape of your atomization function that resemble the shape of your actual signal. There are experiments in the indirect dimension where the actual signal does start from 0 and build up. They're cozy experiments, and so in that case, you might actually want to use a shifted line like that. There are reasons that this Heiser window can be considered an optimal window. It has, in terms of its preservation of the intensity of the signal relative to the sync wiggles in the side, it's optimal. So that's a nice window to use. Nice thing about NMR effects, we can play around with it. We'll show you in the better 2D spectrum. We can just keep playing around with different values until we get what we want. Got a nice looking stuff. Okay, go back to it. We can see again the effectiveness of the let's go to just back to the exponential decay. As you can see here, basically as I adjust that, we're basically increasing the width of the signal and decreasing time. Okay. And off to FT. We'll talk a little bit more about this later, but popular technique now in NMR collection is telling myself I'm not going to spend more than 20 minutes in this month before we get to real data, so we'll try to get through this. Popular technique is non-uniform sampling. The idea in the direct dimension, you have your FIDs, doesn't really matter how long they are in terms of the time of the experiment, because maybe actual FID is a couple hundred milliseconds, but you need to wait a second and a half for the relaxation of the experiment to go on to the next repetition. So you don't really gain anything by shortening that time. But in a two-dimensional or three-dimensional experiment, every indirect FID you collect is. So if you can skip some of those, you're going to save time, and that's the concept basically of that's the concept of non-uniform sampling. So here I've simulated basically where I've dropped out and only collected a subset of the peaks. Direct dimension doesn't matter, but in the indirect dimension, every one of these points that I collect takes time. If I do fewer points, I'm going to get it done faster. But if I do that, what does my spectrum look like? Not so good, okay? Why does it look like this? It looks effectively like I've reduced the signals in stuff. I go to this schedule here. On this sample, I'm talking only 5% of the peaks. People that have heard me talk about this before will be able to answer this immediately. If I increase the sampling rate, what's going to happen to this site? What will happen to this noise? What will happen to the peak? Any ideas? Peaks stay the same, get smaller, get bigger. It's bigger? You see. It's bigger. Bigger. Why does it get bigger? That. You are, but that's not entirely it. What's happening? So it looks like my signal to noise is very bad. It looks like I've introduced a lot of noise in this side. I'd like to say that this is not noise. All this stuff that looks like noise is actually your signal. Imagine that you take a beam of light and you shine it through an aperture. And the light now spreads out in some diffuse pattern. That spread out light was actually the light we started out with. It's just it did not go straight through. Which is why when people talk about noise, they often talk about what's called the point spread function. That's actually comes back from optics about how light going through an orifice spreads out effectively, there is this point spread function which is based on the sampling schedule, or actually the Fourier transform of the sampling schedule, basically spreads our signal out. So this guy here looks like a value noise is stuff that effectively should be where the signal is. So we can see that now if we actually go back to the sampling schedule and increase the fraction of data points that are collected. So we can see is we actually make our scale bigger. So go all the way up, auto scale, and now let's go back and make it worse. So you can see the signal actually gets smaller. What's like a noise gets worse. So really what you're doing is you're spreading your sample out, spreading your signal out in places you'd rather. We can fix that. And this is lots and lots of people writing lots and lots of publications over the last 10, 15, I don't know how long we've been doing this now. 20 years. We can go to advanced operations, sampling schedule, and there are a whole series of operations. I've got one called grins. And so if we go back and look, let's turn off the Fourier transform and turn off grins, looks like that, turn on grins, we basically approximately filled in actual signal. There's a whole series of different operations. Smile from NIH VAX group, Neste, Michelle Gill. We implemented here this GRINS algorithm, my recursive algorithm for acronym for GRINS is not smile, because it's kind of like smile, but not the same. Question, yes.
Can you talk about this? So,
Yes.
is your set simple? So. That's what I would say. It's like,
So the sampling schedule, basically, again, remember, it's not the direct points in the FID, directly detect. It's normally you'd say, you're going to collect one FID, you can increment it, delay the experiment, collect another FID, increment another one, and eventually you're going to do the Fourier transform in that second dimension across the points. You're basically skipping points that you collect, and there's a whole series. There's a cottage industry of people that come up with algorithms to computationally fix this issue, and there's a cottage industry of people that come up with optimal schedules. One of the most common ones is called Poisson gap. You'd like to have a sort of randomization to the schedule. You'd like to have more points already collected at the beginning because your signals always decay away. So why collect a lot of data points out where the signal is effectively decayed away? So there's a whole series of schedules. So computational analysis decides schedule, what values to collect, what not to collect. On the Berkeley minute, you find a file called the list, which is a literal list of the actual increments that should be collected. And then there's a series of computational tools that go through. A lot of them, like grins and smile and Neste, are all iterative. They keep going a series of forward and backwards, inverse Fourier transform. Each time it's improving the signal that we get, recovering basically the values that were never needed. Okay, so questions on that. That's basically a little bit of practical in the sense that all the processing in NMR is by putting in these operations and setting appropriate parameters. Theoretically, we talked a little bit about FT, zero filling, optimization. This one of our goals in NMR development was to make it sort of visually useful, so you can actually look and see what's going on and play with these parameters. Okay. I'm just going to quit and then just restart. Let's actually process some real data now. So I'm going to go to open files in NMR effects. My theory has always been that doing things one way is good than doing things 5 different ways. you can open a file by going to the file menu and we open. You're navigating and finding for a Brooker file, it's either an FID if it's a one-dimensional file or an SCR file if it's a 2 or 3-dimensional file, and literally opening up that file. You can drag and drop, you can just drag those files onto the Spectrum window and it will open them up. There's a data set that the browser will show, which will find all the data sets in a directory like you just started interactively. Browsing a little bit more like let's open one. We'll do one first mechanically here. Open. Go to demos, NYSDC. And let's start simple. This is the one-dimensional spectrum. When you open up an FID, slightly annoying, but it's always going to ask you for the name of the file that put it. The process file is going to go in a file that if you've already processed it, it'll say, oh, you want to use this, the name you've already chosen. That basically, this is the name, and it's going to kind of try to create some sort of name, but I like to give them sort of more meaningful names that you remember, that HMUC on sample X or whatever. Opens it up. If it's a 1D or 2D spectrum, it will automatically come up with a processing scheme, which is why now we see, we open an FID, but we see spectrum. Come back to parameters. Let's go to look at parameters. Parameters just a list, the pulse sequence, the solvent, the temperature was collected at. We'll come back to these again in 2D a little bit more. Spectrometer size is referencing by default. It's going to try to figure out from Brooker parameters what to use. But you can do things like say, I want the ppm in the center to be water. And it's got a little calculation to figure out, give the temperature you're at, what's the chemical shift of water at that temperature. So you can do that. It's going to insert a series of processing operations that we talked about. Just sort of default things you might want to use. Signal suppression, optimization, zero filling, Fourier transform, phasing. It'll try to auto phase the spectrum. So this, boom, looks pretty good. Pack a lot of line. It's a plant-derived compound natural product that has some maybe anti-cancer property. Again, we can go in with the interactive tools here. We can go in and say, well, let's zoom in. If I'm going to select a mouse node, I just drag across, and I can zoom in. I can play around with optimization. Line button bigger or smaller. I can turn off central decay by either function. You can very quickly interact and go around and optimize. One down, the buttons on the side here, refresh just redraws in case it didn't refresh after something. Full takes you to the full display. Expand if you're in crosshair mode. Put up the crosshairs. It expands, it's going to expand to that region. Zoom in takes you in, zoom out takes you out. Auto scale, higher takes you up, low takes you down. You can do things like click on the axis here and drag around. Using my mouse, just zoom in, zoom out, and the gestures. If you're in the selector mode, you can just drag across. And anybody do 1D spectra? Just look at one good old session. Excellent. Yeah.
I was gonna ask,
Yeah.
ways to save the parameters to processing parameters and.
Yeah. So let's go look. When you process, if it's successfully processed, it doesn't have an error, it's going to create a file called process.pop. It's a Python processing script. You can't execute it in regular Python because it uses tools inside the NMRFX, but it is basically Python. If I open it up, you can see the commands, FID, to open the FID, create the data set, acquisition, order parameter, not really using right now. Brooker has this issue of, I didn't really show you, this sort of build up at the beginning of FIDs caused by the digital signal processing. If CSD is true, which can control the GUI as well, if it uses one algorithm, have false or there's another thing, labels, acquisition sizes, the real stuff comes down here. So dimension 1 means that operations on dimension 1. So here's the water depression. It was inserted by default, but it was disabled to be equal to true. I sort of inserted a lot of things you might often use, but like water suppression, you maybe don't necessarily want on. So it's sort of put there, turned off. The Kaiser window function, 0 going, FD phase, and then finally at the end run. So in fact, you can actually execute this. There's an ability to run on the command line. So you actually could execute this on the command line with one NMR that's program. Kind of like you do with NMR TypeScript. Yeah. If you open up a file and it finds this process.py script in that directory, it will open it up and we'll get all the processes back. You can also go in the GUI under the scripts menu. Here we can show the script. We can open an existing one. We can actually go to a different directory where we maybe save one and apply that to this stuff. We can go open it from another directory. We can save it under a different name with the save as. I like actually when I get processing working, I will say something like process_work, and then I can go mess with it and always remember that I can go back and load that. That I saved. Okay. Lots of things that will, won't go in on, 1D Spectra. We can do things like could integrate and see go through and integrate the spectrum, giving this intensity at the bottom or integrals at the bottom. You can do peak pick and it's going to go through and automatically peak pick the spectra, and there's an analyze mode. We'll go through analyze it. Analyze, and it goes through and actually groups things into things like triplets and doublets and lets you interactively jump down. If you're a chemist publishing on some molecule, and you go to analyze and say display report, and you get this little string of text, which is what you're publishing in JNet 10. You can use that, or if you're going to the reader, you can choose the format for text, and you get sort of the format. For that, you can go in and interactively change all these things. So let the mouse hover over here, and I can go in and say, "Oh, I'd rather than a triplet, I'd rather do that as a doublet of doubles." That didn't work right. Doublet of doubles. Huh? How do I repeat that? I've probably using trackpads, right? Nice. Go back and change it to triple. So you're going to interact with it. Okay. That's basic 1D processing. Let's go on and use 2D. So I'm going to, you don't have to quit, but restart. But I like in a demo just to make sure we're sort of starting with a clean slate. Okay, 2D spectrum, pretty much the same. So let's go to the dataset browser this time. And let me find the folder that has its data in it. So that's NYSDC24. Open that. Okay. So in this mode, I get I open up a folder, and basically it's going to find every NMR data set. If you open up your home folder on your computer, it will find every NMR data set anywhere on your computer. Actually, it may take a while, and to drive this. You get the path to the FID relative to the path you opened up. The data is selected under data set. If it is going to process data set, it'll appear there as a combo box you can select because maybe you process multiple times. The most recent one that you've collected or processed will be the one displayed by there, so the pulse sequences and other dimensions, spectrometer frequency, and the text files. You can sort of quickly scan through and find files you want. I'm going to go to ubiquity relaxed data one, which is basically just an HSQC experiment. I have two choices. If I click on data set, then I'm going to open the process data set. If I click on FID, I'm going to open up the FID. And again, it's going to prompt me for a name. And it's going to set up processing script. So let's go look at parameters. Before I do that, there are three modes that you can sort of put in display in when you're processed. And those are controlled down here at the bottom of this thing. So FID, that's the FID. This is a n-dimensional experiment, 2D. So I can go to this navigator and I can basically slide through, basically see all the FIDs that are collected. I won't talk about it here. We actually have, sometimes you're doing a long experiment that takes like 3 days, and maybe there was a bolt of lightning Saturday night at 11 p.m. and that one FID collected at that time is ruined. Pretty much your experiment is held ruined. We can actually go in and find those corrupted FIDs, mark them. And what we've done is other people have done the same thing. Basically, you can think of this as a notice processing. You can pretend that that is a sample that you didn't collect. And you apply notice processing to it, and it basically replaces that corrupted FID with basically the simulated one that comes out of the notice processing. So it's a way to recover experiments that have been corrupted. So that's FID mode. FID with ops is basically the FID and then the series of operations that apply. So we're not doing the full processing. We're just sort of showing, take this vector, apply the zero filling, the apodization, the Fourier transform. And so it's a nice way just to sort of get a quick look at all those. So one thing Art talked about, and this is now we're trying to get into some of the things that he talked about relative to what we're showing you today. So we talked about these different ways of doing HSQC experiments. In particular, he mentioned this PEP, preservation and equivalent pathways. He also talked about things like hypercomplex data. So depending on how we collect the data, there's different ways to process. So we give you a series of choices here, and sort of the classic sort of so-called states method is hypercomplex. Basically, you collect one FID, and that's going to be real values. You collect the next FID at the same P1 increment time. That's sort of imaginary values. You do a Fourier transform across the indirect dimension using those real dimension values. In the echo, anti-echo, or PEP method, you can't simply do that FT. You have to do some combinations of the data. And so typically what you do is take the first row and subtract from the second. That becomes your new sort of first row, and take the first row and add a second. That becomes your second. So as Art pointed out, that gives you a significant improvement in the signal to noise of the spectrum, because the original ways of doing HSQC effectively, the magnetization gets split into two pathways, and you lose the one pathway. Here you sort of recover that. And so how much signal improvement, other than, as Art pointed out, other than the losses from any additional pulses you might have, what should you gain in doing that? What factor of improvement is signal to noise? Root 2, yes. Basically, kind of the same as always when you're averaging NMR signals. The actual signals go up proportional to the number of values you average in, but the noise also increases, and it increases basically as root two. So overall, you get a root two gain. So here, if I do the hypercomplex processing, I see that. If I go to echo and echo, we can see that my signals double. So important to get that right. I look at Brooker parameters. There's an FN mode in there, and I look at that and I try to figure out the correct thing to do. But it may be that whoever wrote the pulse sequence may not have done it exactly consistent with the Brooker parameters. So you may have to interactively experiment with this and change it. In a second, we'll see what happens to the actual spectrum gene. Dimension one, again, I've introduced applications, durability, Fourier transform, phasing. By default, I'd be doing applications, sine, bell, squared, because that's what most people using NMR type often use. What are other things that we might want to do to this spectrum? Just simple things. What's this? Solids. Yeah, this is just residual water. Not too bad here. It doesn't really affect things, but sometimes it might. So let's turn on salt suppression. I insert that as an operation because it's great. I have not checked it, didn't turn it on because you may not want it on. We have to have real signals there in a second. So we just click it. And now that signal is gone. You can fine tune. There's a window parameter here that the smaller that is, the wider an area. So if you get too wide, you're suppressing the whole spectrum. You get too narrow, you have some residual water. There's a shift, so you can sort of move it around, and so you want to sort of fine tune it. Smaller so needed. You can put in a second signal suppression. You can any operation. You can put it in with the plus button over there. Second, so you may have like a detergent in there, and so you can suppress the water. You just put in another one to suppress the detergent. Another thing you might want to do this. Is this interesting? Nothing interesting going over here in half the spectrum. So why make your files twice as big? Carrying on, especially when we get something slower processing, why have all that? So signal suppression, let's go to extract region. There's several choices. Mode left just gives you the left half of the spectrum. You can be more explicit. One of the relations when you do that, you have to do a bit of full sort of get the access to be correct. Another option you often use. So look at the spectrum and think, well, if you do left half, you're still getting the water signal in there, and if it's got any sort of decay or wiggles in, maybe you'd rather leave that out. So you might say, okay, this spectrum might go from 5.5 to 1.5, and set this to region. Okay, so now we've got an explicit region. It's good. If you're collecting like the background experiments to show, it's nice to do the exactly the same for each experiment. Remember what you set it to. Be careful when you do it from this first row. You may have weak signals out here that you don't see in the first row. When you do the full 2D transform, you say, oh, there's a signal out there, and you sort of cut off that area. So, and it might be good to process the whole spectrum before you really narrow in too much. So if you're cut off it and perfect signal, you never know there.
Is there a way to look at like two transmissions at the same time during phasing?
During phasing with the when we get into the full 2D spectrum, yes. Yeah. Sorry, yeah. Okay. So this is all in this fit with ops method. At any time, because this auto update is turned on, the first spectrum, but every time we change one of these things, it's going to refresh, reprocess. So if we hit process, it's going to apply the processing and put me into the spectrum mode where we see the full. So there's our HSQC. We'll talk about phasing in a second. Let's just go back to parameters real quick and just, what if I got this echo and echo wrong and did it hyper? See? Now I no longer have proper sign discrimination in the indirect dimension. So all of these are duplicated. So if you see that, double check this acquisition. Okay. Phasing is pretty good here. We could go, and if I go to dimension 1 and click on phasing, it's going to insert, it's going to turn on a slice there. And now as I slide through the slice anywhere I can see, if I put up, can I get a second slice in phasing? I could. First thing we want to do is go to where you set the pivot and set that at crosshair. So is put up these green triangles. Pivot. So we have two phase items to set: the zero order, which applies a phase correction across the entire spectrum, and first order, which linearly increases across the spectrum. So by setting the pivot on this peak, I should use this one, it's a little bit bigger. I phase that with a zero order phase correction, and then so I can just fine tune this a little bit, get it where I like it. And then I can take and put my cursor up, say on a peak on the other side of the spectrum, and then use the first order phase correction to get that. As soon as I let go, it's going to redo that, which I think so. Of course, I can process that. Go to attributes and go to slices and turn on slice 2. Go back to process. Well, let's see. Yeah. So now I've got 2 slices out you can see the phase of the we have pretty good auto phasing. The spectra are nicely collected, good quality, and this has the special combination of being ubiquity and Shabbat. Put those two together, they're good stuff. But if we go to the full data set, there's a full auto phasing. If that's turned on as an operation, then after all the processing, we'll go and apply automatic phasing to everything. So if I go back to dimension 1 and I turn off, let's go to full data set, turn off this auto phasing, go back to dimension 1, turn off the phasing here, okay? Note the peaks are now out of phase. Go back to full data set and turn on this auto phasing and boom. Okay, so it looks good. So you can create, if the spectrum is good, you can, this full auto phasing is about as good as I can do manually. First order, so dimension, you can, dimension 0 means do the first and second dimension, or you can simply apply just to the first or second dimension. Have the first order button turned on, it will be a lot of phase first order. So, okay. 2D processing. Let's do one NUS data set, and then we're going to move into assignments. I'm going to use my data set browser. I probably should. Let's do that. Let's go back. Data sets. It remembers where I was. I mean, index. The index and finds everything. If I go to HNCACB experiment and click FID, then I mean open up the FID. 3D experiments and more, I should probably be more aggressive about this, so to speak. I don't automatically set up a processing script because I have less confidence that I'll get them right. But typically, if you go to the scripts menu and say auto generate, it will then try to automatically generate a script. So, and that's usually pretty good. So if you do that, and it detects that there is a NUS list file in the directory, and there's a broker parameter, this sort of messed me up a while, because I used to just assume there's NUS list was NUS, but in fact people can have a NUS list file in their directory and not collect it as NUS. And so there's a broker parameter that I now look for and say, okay, it was a release. If you do that, then I insert this indirect matrix processing, which has several sub commands. Zero filling happens during this processing. Apodization happens during this processing. Phasing, this is a bit of a pain because our NIST processing algorithm grins really only works on phased data. So you may have to kind of process once and figure out what the phases are and then put the correct phases in here. Haven't come up with a good workaround that so that it actually will phase the spectrum while in the processing. And then which processing method we have NSA, grins, or IXC. I guess like the following commands. So I'll just click process, so we'll take a little. Let's actually. But go to dimension 1, you'll see important thing in dimension 1 processing is that it did this extract a region because the NIST processing is basically takes the one-dimensional spectrum and for a 3D spectrum, it's grabbing out two-dimensional matrices at each data point and applying in this process and that. And there's no point in doing all that on the signal to the right of the wire where there's not going to be a signal. It's just going to slow things down. So let me just hit process. It always asks us for a name of the file. So this bar across the bottom is zipped across almost immediately as it did all the processing in the first dimension. Now it's doing this NIST processing in second and third dimension. It's really fast because we sort of parallelize all the processing on this. So if you have a 10 core map or whatever, it's going to use new processing. So it's reasonably quick. So now it's going to do extract each plane, apply this NIST calculation to basically fill in the values you didn't measure, and then it's going to do the normal processing on the second and third dimensions as you would have if it was a regular sort. So as soon as it finishes the process through 3, you'll see it sort of fit for doing the second and third. Almost. Zip, dimension 2, dimension 3. Okay, so a 3D data set, basically, I'll just close out my processor tab here. We interact with same way as 2D, except magically will appear another control over here, Z, and Z has options like default, so that's going to show me all of the dimensions, what's processing and keep lowering the contour level or what's slaying or the contour level. See values. There's also an X and a Y, and I can change Y to carbon 13. So now I've flipped the data set around. So now it's proton on this axis, carbon 13 on this axis. It's an HN, CA, CB, sperma. What's wrong? Where do alpha carbons appear? Yeah, 50, 60 ppm. So alpha carbon. Where do beta carbons appear? 20, 30, 40, 50. Don't see them. Why are they not there? Because even though Art has asked me about 4 times to do this, I have not made it the default to show negative contours. So let's go over to this attributes tab. And it's on a list. We have lots of attributes we can change, one of which is contour appearance and checkbox to display negative contours. Okay. So now we get and it looks pretty good. And there's not a lot of, we could, if we had more time, we could reprocess without doing this process. You see all the streaks and run through it. This looks like a pretty good spectrum. So this processing worked reasonably well. We can do things like I can go to the center plane. I can use the arrows to go up and down through the planes. Any orthogonal view, proton, nitrogen, carbon, nitrogen. I feel like with the NUS stuff, I like to put nitrogen on the x-axis and carbon on the y-axis. So that's kind of where, that's the indirect dimension where all the NUS sort of artifacts are going to appear. So you can sort of see them nicely. There. But that's NUS processing. It's basically the trickiest thing, like I say, if I go back to the processor, is getting these phases right. And what's the best solution for that? The best solution is to set up your experiments. You don't have phase corrections in the indirect dimensions. If you are zero, okay, or you're some fixed, we're talking about sometimes doing the 180 degree, minus 90, 180. So if you set the experiment to that, then boom, you can set those up. But, you know, ideally, you'll set up the experiment so you don't have, you know, first order phase correction of 33 degrees and have to figure out what that is. First order, the first dimension is, you know, is easy to fix. But this indirect dimensions with the NUS, it helps if you are set zero phase. Okay. So we've processed the FIDs, processed the one-dimensional FID, processed two-dimensional FID, processed the 3D NUS experiment. Let's actually try to do some assignments. How many RNA people are in there? One, okay. Your protein, a good chance of getting through this, because we have some really nice RNA stuff. I don't know who all's out there. Ring in Zoom world if you have questions. Okay. I didn't get completely organized with getting this going. Okay, let's talk about projects. So if you're going to work on anything more than like 5 minutes, it's good to create an NMR project. And that's very easy. You have the data up in display, you go to projects and you say save. If it's the first time, it's going to prompt you for a name of where to put it. Some of my colleagues like to give them names that end with .NAP for NMR fixed analyst projects, so just to remind you, that's what it is. A project is just a folder on your disk, and it has 5 subfolders. I'm going to try to simplify it. So the data sets, any data set you open in the project ends up getting what's called a hard link from that folder. So that folder looks like it has the data set in it, but it's not duplicating the original where the original data set is. And if you delete the original data set, it is actually still in your folder. So it gives space, but lets you get rid of the original stuff. There's a star folder because all the ancillary information we develop, assignments, sequences are going to end up in a VMRB star file. There's a window folder. So if you save a project and you have like 5 windows open in different orientations, when you reload the project, you're going to see those same 5 windows and with the same data sets, and that goes into this Windows folder. There's a peaks folder, which actually gets all the peak lists written into. Well, that's redundant with what's in the star file. When I read it, they're there, so if you want to go in and use some other program and grep through or look for peaks and write a Python script, the files are there if you don't want to learn how to read a star file. Okay, so I'm going to open up a project I saved today, 1VENYSEC1. So there's now, I can't remember the web link, there is a group that has set up a 100 protein database. And what we've done is we've downloaded those and we're playing around with those. So they have complete all the assignments. A lot of them came from the Northeast Structural Genomics project. So they have backbone and side chain and nosy experiments, basically everything you need to solve a structure. So this, I kind of move on from ubiquitin a little bit. So instead of using the ubiquitin as my demo, I'm picking one of these that we've been playing with, lately and testing things out. Okay. And we're not gonna have time to go through the whole thing here, but let's talk about the steps involved in assigning a protein. So step one, which you're now all experts on, process your data. So you have typically our talk about some of the experiment stage, NCA, NCO, CA, HNCO. We're going to use 6 different experiments to give you the carbonyls and the alpha carbons and the beta carbons of a given residue and the residue for it. There's 6 different experiments. There's a lot in here because when you load these projects, they have a bunch of assigned peak lists in there already, so you guys can use to be able to do our assignments and then check to see if we get same assignments. So thing one, I haven't really shown you peak. Let's real quick. Let's open up a new second window. You can have as many windows as you want open in NMR. We can go to show data sets here and say, let's find, say, the HNCO. These are actually, we're all Sparky formats, but we read the NMR and Sparky and Booker 1R, 2R, etc. Files, quick draw. Here's HNCO experiment. I'm going to come over here to content, and in content, I can decide what data sets appear. This second, I can drag them down. I can have as many data sets as long as they're sort of compatible, the same axis labels. And I can have heap list in. I'm going to remove this heap list. Now, if I just refresh, no peaks. There's a bunch of different ways to peak pick. I can put the cursor in the peak pick mode and then just click on peaks and it'll pick them. I can come over here to tools and choose the peak picker. And I'm going to turn off auto name because I want to give this some name that doesn't conflict with what I'm already using. I'll call it HNCO test. Region, I want to pick a box, which would be if I put up the crosshairs, fix it in the crosshairs. If I said window, fix everything in window. Mode new, that peak list doesn't exist. I click pick and it's peaks. The very simple peak picker, just find the local maxima in the spectra. We have a more sophisticated peak picker in a forthcoming release. If I do this a second time, it's going to give me an error. It's going to tell me that the peak list already exists. And so now I've changed the mode to replace it if I want to pick it again. But then I actually gave one of these demos and somebody spent like an hour assigning an RNA, working through it, and then click pick again, and then repick and blew away everything they did. So now we say you have to explicitly go into this replace mode to actually repick. That's peak picking. You know, in the selector mode, we can zoom around, we can click on peaks, we can drag them around, we can hold down the option key and resize them, set. On any peak, I can call up this inspector and I'm going to go and manually assign things that I can assign 32H from set. So that's peak picking. Like I say, with this. In the pick mode, you can also just sort of literally drag across and let go, and it'll pick whatever's in that region that was in 1D2D. Okay. So we collect our experiments, our 6 experiments. We go into what I call the configure mode here. Here's a list of all the peak lists that are actually open currently in this project. And what I have to do is several things to set things up. I have to tell NMR what these experiments are. Like CBCACO, what is it? We have what we call patterns that explain what the data is. So I can actually click on the road here and call it the inspector. And under reference, you can see that there, for each dimension, there's a pattern. So I stands for residue, H stands for atom. So the HN dimension is going to have proton. The C dimension is I-1, So if the proton was residue 35, the carbonyl is residue 34, ionized slot. This is actually the CDCA, and it could be a CD or a CA. So there's a little pattern to specify. The bonded one there says that the proton is bonded to nitrogen. So there's a little schema to explain what's going on in an experiment. And mostly, if you open up a data set, you can just sort of click from a list of choices here and select the correct name, and it will then populate these. You're going to avoid going into typing. Let me go to one, which is a little. That was CBCA. Let's go to a slightly more complicated one. The most complicated one we have here. CBCA NH. Okay. We're kind of zip through some of these. Let's say a little bit more. This one, I minus one. So the CBCA NH experiment can go from the HN to the CA and CB of that residue, but can also go through a two-bond coupling to the previous residue. I minus one experiment, like the HNCO, you can actually write the pulse sequence to explicitly go through the carbonyl, so they're unambiguous. Experiments to get in the eye, the same residue, because it is a weaker two-bond coupling, you can also pick up more weakly the signal from the previous residue. And you can write these experiments. Remember, the minus here, the peaks, because some were negative. The minus after the CA means that the CA peaks in this experiment are going to be negative and the plus means are positive. So if you want to kind of automatically type them, I can look at the sign. That's kind of took a while process to say that other days that it wasn't working right. Then we realized most people collecting the other way, CE's negative and CA is positive. This data set, for whatever reason, was inverted. So we had basically changed from our default pattern. Okay, so that's the pattern. So each of the experiments we want to use, we've got a pattern. We put the checkbox over here to say that it's active, meaning we're actually going to use this in the assignment. We have tolerances. Basically, whenever we're comparing one residue with another, or another peak with another peak, we have tolerances on how close. Like if you have an alpha carbon from one residue and the alpha carbon from the next residue, are they close enough? That's set up with these tolerances, and you can basically have a few choices here. Tolerances. You can sort of calculate on which for the average line width of all the peaks, and basically the tolerance on the line of the peaks. Set the defaults, use these values over here. You can or some default values you save, you can actually explicitly put in tolerances over here and use those. So those things you need to configure. That means that. Okay. Once you've set them up, then you put this set on. I would just guess I would not use. If you only have a few data sets, then right here, you guess it'll sort of HNCA. We have all these duplicate lists, so that's not going to work. Eventually, you get it set up here, and then it's going to set. We go back to the helm. I take us back to this slings. Little detour. These are the San Juan Islands. I grew up spending most of my summers living on where I'm taking the picture from and working on for 7 years, working on a commercial salmon fishing boat there. I like the water and oceans, so I call this tool runabout with the idea that NMR spectra I think of as being oceans of noise. And scattered in the noise are islands of signal. And so runabout gives me an efficient way to zip around through the islands and find things without having to wade through acres or kilometers of noise. Okay. Go back to the. So we have peak lists. We have arrangements, and we have is. So let's okay. So what do we have? So under arrangements, I give you different ways to look at the data. So giving ideas, we're gonna have to wander through all this oceans of noise. We can sort of zoom in. So in HT mode, we're going to see proton on this axis and the carbon on this axis, and the plane is going to be the nitrogen, okay? And I selected one list here, the HNCO is sort of a reference list. And so if I step through the peak, I'm at peak 0 of the HNCO, and I say, okay, what's the proton and nitrogen frequency of that HNCO experiment? I'm going to go to the plane of the nitrogen. I'm going to center this window around the proton frequency of that CO peak, and then I'm going to show all the other peaks, the full carbon dimension for each of those. We have other modes that we use here. Another one that's actually useful to do right at the start, HM, but here's now the proton nitrogen view of all these peaks. Why would we want to look at that? This is really important right at the beginning. Make sure all your data sets are referenced correctly. So the little blue lines across at the center, we like them to be all the same for all the spectra. We have an auto alignment tool that should under action sort of auto align and sort of go up there's manual ways to reference things, but that's like step one. Make sure all your spectra are correctly aligned. Okay. HN full gives us full view of all this, whole thing. It's a little easier if we have a big screen. We can go into cursor mode or crosshair mode here and click, and NMR affects all windows that have compatible axis names or the cursors move far away. So you can sort of move around. Just again, make sure that finding one peak in one spectrum aligned with peaks on the other side. Another view, this is HCNC. So now we have, in this dimension, the proton, the x-axis centered, the nitrogen on the z-axis, the carbon up here. Here now we have the nitrogen on this axis, the carbon up here. So basically, this is this peak sort of rotated or orthogonal view. The nice thing about that, you can sort of step through quickly all your peaks and be able to have two orthogonal views on. So in this mode, we're just going to like step through each peak. So I'm going to each HN0 peak. And I'm just looking at my spectrum. I peak picked them all. What do I want to look at this year? Are my contour levels good? And this is something I didn't say. You want each spectrum you want to look at, get a good contour level, and then under attributes, there's a store button, and that saves that contour level with that data set. So whenever you put that data set in a window, it says, oh, I want to be contour level 45. So you get these things set up right so that whenever you go to a new data set, it looks good. So we step through, yeah, this is a nice data set. I'm seeing reasonable number of peaks, not a lot of artifacts. So I probably picked at a reasonable level. And that's good. Okay. We can start going through our actions now. Align, I said, is useful if you're not perfectly aligned. We'll try to align all the experiments to the proton nitrogen frequency of the reference list, which I can configure. I set the reference list to be HNCO as a reference. Now, another action, filter. A little riskier. Filter basically says, if you have a peak in the CBCA experiment and it doesn't appear in the HNCO at the same proton nitrogen frequency, it's maybe an artifact. And we just get rid of it. A little riskier. It's not, some people do, there's an alternative where you're peak picking. So you only pick peaks that are in the location of the proton nitrogen frequency of the HNCO. So this is sort of a post type of process. Okay, actions. Assemble spin system. Gives me a little warning that if I've already done some next steps, it's going to undo them. I should have pointed out a couple of things in what kind of world we need for this. And we actually have a whole tutorial to take you through this. At some point I read in the sequence of the protein, just a file you can sort of piece in like a fast-dating single letter, load in a file, which is a 3-letter amino acid code to get that in there. You get the sequence down here. Assemble basically finds peaks that share similar proton and nitrogen frequencies based on those columns. So then it links them together and we spins it. So now instead of seeing a peak number, we see a cluster numbers. a spin system. So all the peaks that are 0 have been linked together, all presumably come from the same share an amide frequency of the same amino acid. Okay. Assigned atom type. So we have, give me an answer. We have a peak, so you know, this peak in HNCO, pretty obvious that it's a proton and a nitrogen and a carbonyl carbon. These peaks of the HNCA, well, okay, we know for sure from this pattern is that they're both CA, but one is the CA of the previous residue. And the third from the left, top, CBCA and H, there are 4 peaks. And you can see at the top, they all expect a label what you expect, CACB, lowercase CACB of the previous residue. We should expect 4 peaks. We don't know which ones they are. Okay. So the next step is assign atom types. There's another little line. And now, as I step through, now you can see up at the top, the little green bars. That means the 0 means that expected to find 2 peaks, that you -1 didn't find one of them, or +1 to find an extra peak. So now we've typed all these. I will say, cautiously optimistic that we've come up with an idea to do away with all this. Multiple people have said, why did we pick this? And I think I've gotten out of the way to do this analysis where we don't see it works in our simulated data and flipping through it. So this may change. One thing that's driven us in development of this tool is that we've never tried to be fully automatic, because I've always felt that if it's fully automatic and then it fails, you're kind of left with not knowing what to do. We'd rather have a nice interactive tool and then put automation in there, but then let you fall back to the interaction. Okay. So we can step through. At this point, you're just going to step through and come to values where there's red and it's missing 2 peaks, and sort of think about it, dig down in the noise, maybe find peaks, add them in, or there's too many peaks, and you go in and maybe delete, find what looks like the weakest artifactual peaks. We have actually in Cincinnati trim, which will sort of get rid of the weakest peak that you don't expect. So you can go through and do all those actions. Okay. Match adjacent. And let me change the arrangement that we're in. And let's put us into CHIJ. Or this is maybe a little small to see. Okay. This is an HNCO of some residue. It's actually the CO of the I-1 residue. Somewhere in the protein is a CO in an HNCA CO experiment. It should be that same CO. And what we've done with this matching is give us a list of possible matches. You can see this C1 match this peak here matches this peak here. In the CA, I don't know if people are better to point up here. In the CA, you can again see this peak here matches this peak here. CB, CA. These two, a CB and CA, and the I-1 residue match up with the CB and CA of a previous residue. This is the fundamental way that you assign backbone protein. You have these sets of experiments and you overlap on one residue. You scan across all the other spin systems basically and find ones that have compatible matches. And you can go the other way. So I'm over here and say this carbonyl matches to this thing. These are matching pretty well. There is a little trick. If you go to configure, you click the unified limits. when you collect these experiments, it's nice to collect them with the exact same sequence and reference frequencies, but sometimes they're off a little bit. And if you do that unified limits, then the spectra are sort of aligned in a way that if these guys are the same chemical ship, this green line is going to go straight across. Okay, so it makes it easy to see. I will say that this project, we've done some cleaning already, so I should really have time. We've gone through, we've deleted some artifacts, we've picked a few extra peaks. You're basically going to step to the clusters and sort of, oh yeah, they need to add an extra peak here, delete a peak here. Once you get through that, so in this mode, we get this row, you can see across here. These are the chemical shifts of one cluster. So this is, if I did my atom type correctly, the CA is at 41.4, CD 41.4, CA 53.1. This previous cluster has a CD at 41.4, 53.1. So they're in very good agreement. And given these chemical shifts, I have an idea what the amino acid is, because carbon, alpha, beta appear at characteristic frequencies for each amino acid. So I get listed most likely aspartic acid, one appears most likely phenylalanine. The theory colored in descending order. So, most likely Eve is a little bit darker. So it's a little less likely to be the correct one. What we're going to do now is, we're going to have enough time to sort of throw this carefully, but if we look at that and like it, I'm going to click this checkbox and say, okay, I'm going to link those two together. And so now I have not only the chemical shifts of the I and I-1 residue, but the chemical shifts of the previous residue, and I can look through the sequence and say, those chemical shifts are consistent with this position in the sequence. And so that's the only place that you go. And that's kind of a characteristic that shifts. Right. And then I can click on this previous residue and say, okay, this guy looks visibly nice. It's got a score here, minus 147. This is actually the scoring is now based on paper from Josh Vaughn as a Bayesian calculation of what chemical shifts ought to be. Basically minus 200, minus 250 for the end. Because you get a confirm it. You can see I grew a little bit longer. I go to the previous residue and say, oh yeah, it matches up. This RAB means it's a reciprocal match looking both directions. They're consistent with each other. It's available. I haven't assigned something else. And B viable means that there is a place in the sequence that I would link this up. There we go. I confirm that. So you can see, boom, we're gradually assigning things. So if I can do this, I can. Okay. So let's go to under spin system actions. Let's go to graph matching. And I'll just leave these at the default values and click match and then talk about that at state. These are all the clusters. And you see, as I assign them, it's sort of, these are now fragments. These guys are linked 136, 138, 31.5. They're linked together. They appear up here. What we have is what seems like a trivial problem. We have spin systems and we have amino acids, and I want to have an optimal match. I want to be able to draw a line from this cluster down to a given amino acid. That's in the computer science world, that's a bipartite matching. We have two graphs and with nodes and a vertex between the things. There's an algorithm called the Hungarian algorithm and various other ones that optimally do that. Find the opposite. So we put in a score, basically, how good is the match of the chemical shifts of this spin system and this amino acid? And come with optimal matching. That doesn't work. I mean, it doesn't work. The reason it doesn't work is because we have the same amino acid appears multiple times in the sequence. There's lots of variability in the chemical shift, so that doesn't work. So another way to do things is But some other groups are doing the genetic algorithm. You come up sort of with various algorithms, you sort of randomly assign values, and then you sort of mutate them and change them, and we have some score. Not how good is the match, and do they overlap correctly? Is this sort of score here, one residue overlapping another one, good or not? We've decided to sort of combine both these ideas. We use this bipartite matching, and we generate thousands of possibilities. Each time we sort of randomly change how good what the weight is between each value. So the next time we repeat that algorithm, we need to get a slightly different match. That then becomes the population that goes into this genetic algorithm that mutates. So the nice thing is that all the initial things aren't random matches, they're all things that are inconceivable. And so that's what it's doing over here. It's got a score. I've told you to try it 25 times. Repeat this 25 times. Each time, it's going through a bunch of generations of natural selection, basically to mutate these matches and come up with the match. And we didn't really have time to watch it, but the score kept getting better. And eventually, okay, it's 25 times. Each time it went as many as 2,000 generations, but if it was 200 generations, it doesn't improve. Quits. Okay, so once it does that, there's a sign button appears, and we click a sign, and boom. Everything is covered, every amino acid is covered here, is been assigned. Has it been assigned correctly? And you can see again all these friends have been linked together. The color codes, you can see this sort of whatever this tail green is sequence, so it is tail green sequence. So we basically, while I was chatting there, we assigned whatever this protein. The nice thing I say about our tool is that although it's not perfect, but we're not left in. Like I say, okay, this place is like, you know, like why did it go? Why did it do a stretch here, any decay, and then there's elucidated. Why didn't it actually complete that? So I can click on these and then you actually go back and look at the data. I can find places where it didn't assign anything. There's some tricky areas here. G, S, 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 G, S, F, G, S, and a similar sequence at the end, S, S, G. But basically, we've assigned most of the protein. We can do some little things. I guess we have 3 minutes. If we go to this atom table, you can see now it's filled in ppm values for the assignments. The rough info was initially started out this matching basically started out with BMRB statistics on like where is an atom. If you actually have like a homologous protein, you can actually put in reference values for that, and then the error value is going to be narrower for that assignment. We can do things like there's wax plot. Didn't talk too much about referencing, but this is a plot of the delta that's behaving in this side of the CD, and where these one slope is in area of helix and the other is in beta sheet, they should intersect near 0 if you correctly reference your date. So that's not perfect, but pretty close. We in fact had trouble with some of these 100 dB proteins. We found they're off by 2.7 ppm when I do that, and that's a classic mistake in Brooker systems that if you reference with TSP instead of DSF, you get a 2.7 error.
What are the 2 beats in the lower right that are placed on?
Yeah, good question. Could be wrong. Simon, that's the sort of thing you look at this. I don't know if this will get a guide where you can click on them and see what they are. You should be able to. We did this assignment pretty quickly. We have some ways now, some nice things where we can load in assignments from other files, and we've got some nice plot tools here, so we can say plot. assign a chemical shift with say a reference value. These are BMRD values, so they're not right, but if you pull in, say, the assignments, somebody else has done this protein, you can sort of do plots and see how good the correlation fits out, right? Things like that. I'll show one more thing because it's kind of fun. We go to the sequence viewer. This will work. We can do lots of a little things that are sort of common, like I want to show this looks for RNA or protein. We can choose different atoms, and so we can get a deviation basically of the assigned chemical shift relative to average values, which indicates helix sheet. If you come down here, got this residues. Mouse problems, sequence viewer, sequence viewer, residue order value from that on. Right. That's a measure of order disorder. So we can come shift to see if this is the order disorder region of the protein, or we can do secondary structure prediction and bring a deep learning model. And so now this is pretty quick. We've taken that protein, we've assigned it, we've now done a deep learning model, and this basically is secondary structure propensity. So red helix moves G. But there was, some time before to sort of clean up those clusters and do them, but basically we went and, we had to process the data sets, but we saw that pretty quick. So fairly quickly with good quality data, which this is, we can go from raw data to assignments to something about secondary structure. So in the RNA world, we have kind of things don't work exactly the same there, but we have a nice tool. We can actually predict secondary structures of RNAs with a deep learning model. We can then predict what the chemical shifts of that secondary structure are. We can then predict where peaks will appear in your spectrum. And then you can sort of do this sort of slider tool that when you slide a peak from its predicted position on the real peak, you see a whole cluster of related peaks during that atom move close to them. So you can sort of very efficiently assign RNAs. We have to stop, right, Art?
Yes.
Okay. Anybody online, feel free to shoot me email if you have questions about what you did. Same thing, people here can find me at ASRC.
Thank you, Bruce.
Yeah.
Other